Introduction. So in this presentation, I will talk about our work on automated synthesis of asynchronization. This is a joint work with Ahmed Bouajani, Konstantin Enya, and Shuvando Lahiri. Asynchronous programming allows to build responsive software like web programming, where jobs are executed on the main thread and timely costly tasks are executed, such as I/O operation are executed in parallel on background threads, where we create tasks dynamically and we have await instruction that interrupts the execution and pass the control back and forth to the caller. And when a task terminates, the method that is awaiting can resume the executions. Here we have an example of a synchronous program. This synchronous program reads some file using like the I/O method read to end. However, for large file, this program will take too much time because it's blocking the execution. An alternative for this program is to use asynchronous I/O methods with async await primitive. We call this program Asynchronizations. So the mechanism to transform this sequential program to a synchronous program is to replace the I/O read to end to an asynchronous I/O that is equivalent in terms of behavior, and to declare the main and read file as a transitively called the I/O method read to end async to be asynchronous methods, and then add some kind of await statement to say where like the return value of this async will be used. So for instance, for read to end, like the return value of S will be used in the line 14, so that we need to put the await before that. And similarly, for the read file that is now async method, the value will be reused in line 7, so we need to put the await before that. So finding the right placement of await will not be straightforward, because first, some placement can cause data races. For instance, here, we have a data race. If we place the await in line 5, and here line 14, we have a data race on X. So the await of T1 has to occur before the read on X. Otherwise, the read will be in concurrence with the write to X. Also, the performance, because certain await placement can offer more parallelism than others. So we have the observation that it's not possible statically to define a data-free asynchronization that maximizes the parallelism. Usually, like we can think of that if we maximize the distance between, which is the number of statements between a call and its await, this will give us a max of parallelism. However, here we have a counterexample to that assumption. So here we have 3 different programs. We use thread sleep to say that we have some computation that will take 200 milliseconds. And we use task delay to say that we have some I/O calls that will take around 300 milliseconds. So these are 3 different programs. In the first program, we get the maximum, like the smallest runtime if we place it with the furthest possible placement from the call. In the second programs, we need to place await in the middle to get the smallest runtime. In the last one, we need to place await directly after the call. Why is that? So here we have 3 different executions of the first program. In the first execution, which is the first figure, is if we place the await directly after the call, it will take us 700 milliseconds. The second one, if we place the await in the middle between the 2 threads sleep, it will take us 500 milliseconds. And the last one, where we place the await at the end of the method call. So here it's clear that placing the await the furthest possible is the optimal solution. However, the second program will contradict that. In the figure above, we have the await placed at the end of the task. Here, it will take 700 milliseconds to execute that program. However, if we place it in the middle, it will take us 500 milliseconds. Now, if we also take this case and we look at the other program and we place the await in the middle, we will take we will get execution of 850 milliseconds. However, if we place it directly after the call, we get a faster execution of 700 milliseconds. So here we have a counterexample that the distance is not, doesn't give us the criteria of maximum parallelism. So here it gets a problem. We need to enumerate all data for this asynchronization. Then we have some dynamic criteria where we evaluate the performance using, like, say some performance test to choose which one of those will give us the best value. However, the space of asynchronization is exponential. A naive enumeration procedure is to enumerate all asynchronization, and each time to check whether what enumerated is data race free. However, here the complexity of finding an asynchronization is exponential, modulo the complexity of the oracle for checking the data race freeness. Our contribution is an enumeration procedure with polynomial delay complexity. Here, what we mean by delay complexity is the complexity of outputting two solutions that are data race free. Modulo an oracle for checking reachability of sequential program. We prove that this is an optimal procedure, and each data race free asynchronization will be enumerated only once by this procedure. And this procedure will use reachability reduction to find the data race and to repair them. For the rest of presentation, I will follow this outline. I will present the decision, like the reduction that gives us this decision procedure. Then, using this reduction, I will develop a new approximated asynchronization procedure that is sound, and we implemented this approximated method in a prototype tool, and we evaluated on a set of benchmarks. I will present the result of this evaluation, and the presentation with conclusion and possible future work. First, let's go to the reduction procedure. Before presenting the reduction, I will present how we characterize the space of asynchronization. So here we will represent an asynchronization using a vector of integer value, where a value at index I represents the distance between the await I and its associated call. So here we have the vector, the pair 2, 1, where 2 represents the distance between the await T1 and the read file. So here we have two statements, why we have two, and 1 represents the distance between await T and the associated call read to and async, where we have a single statement. Now we represented the space of asynchronization as a lattice of integer vectors that has some partial order relation between the asynchronization. So here, 2, 1 is the weakest asynchronization, because as you can see, like the await are just directly before we use the return value, so we cannot move them further. And 0 is the strong asynchronization, where we place the await directly after the associated call. Now I will present the procedure for going through this lattice and returning the data race free asynchronization. We start from the weakest asynchronization. Then we try, for this given asynchronization, if it may not be data race free, we use a procedure called repair data races that resolve all data races in an asynchronization. I will present this procedure later, where we reduce this oracle that we call repair data races to a reachability of sequential programs. Then, given that we computed some data race free program, we look at its immediate predecessor. What we mean by immediate predecessor is that we take one await, like at each await we move it one statement closer to the matching call, and for each one of those new program, we recursively call the async synthesis over, and until like we computed all asynchronization. So if we take this lattice, we started from like 2, 1. 2, 1 has a data race on the read on line 5 and the write on line 14. So we need to move the await T1 before the read. So this will ensure that the task read file will finish before we do the read. So that means the writes to X will always happen before we read from X. Now we have data race free. we go and compute its immediate predecessor. So here we have two possible immediate predecessor, 1, 0, and 0, 1, where each one we moved one of the away, one statement closer. And by chance, in this toy example, those both immediate predecessors are data race free, and we will call async synthesis over them. So async synthesis will return those two programs because both of them are data race free, and we'll compute the immediate predecessor for both programs, which is 0, 0. However, if you notice something here is that 0, 0 is outputted twice. Once we outputted when we enumerated 1, 0, and the other we outputted when we enumerated 0, 1. So this is a problem. If for a larger program, there is an exponential number of asynchronization, and we always we can enumerate one of them multiple times, this will defeat the purpose of polynomial delay complexity. So here we need to eliminate this. So here we introduce some kind of total order between the awaits. And we introduce a new parameter to the async synthesis procedure, such that the immediate predecessor will change. We give it a new parameter, which is some await statement, and we take the predecessor where we only move awaits that are smaller than the given parameter in this total order. We proved that this has a nice property that work well with our reductions. Is that if you take any two programs that are some immediate predecessor from some program P, the async synthesis over those two programs will never return the same program twice. So you will always return one program only once. So here, if we go back to our example, 0, 0 will never be an immediate predecessor for 0, 1. And we will return it when we visit the 1, 0. So more details about the correctness of this is in the paper, and how also it will work with the repair data races and the immediate predecessor calculation. Now here we always like to calculate the next asynchronization, we only go to the immediate predecessor, and for one of them, when we call repair data races, we are going to get the next data race free, which means that the delay complexity of this procedure is polynomial time modulo the oracle that is repair data races. Now, what is this oracle? So the oracle will take two statements, S1 and S2, that have data race, and it will look at some other statements that are involved in this data race. So here in this example, we have the statement S1, S2, that are one of them does read, the other does write, and it will look at SW, that is the await for the call that contain S1. And it will move that SW before the read to ensure that that call that contain S1, will always finish before you execute S2. So here you'll have some kind of happen before order between those two statements. So we call this SC and S the root cause of the data race that we use it to repair it. Now, how we do find those data races? We do some kind of instrumentation. We compute some new program P prime, such that this program will simulate a synchronous execution of the original program, where we replace all await statement of the original program with some synchronous code, and we prove that the original program admits a data race between the statement S1 and S2 if and only if the new program reads an assertion violations. Now, what is repair data races? Repair data races will go through all the read and write statement in lexicographic order in the original program. And for each pair of statement, it will compute a new instrumented program P prime, such that if P prime reach an assertion violation, it means that there is a data race between these two statements, it will return the root cause of that and use this root cause to repair the data races as we explained above. So here we show that we reduced this oracle to reachability in the sequential program. So that means the output complexity and the delay complexity of the asynchronizations in this problem is polynomial time modulo and oracle for reachability in sequential program, which for finite state program is p-space. Now, for this p-space hardness, we reduce the reachability of sequential program to our problem, such that a location L is reachable in a sequential program if and only if some sound asynchronization of some asynchronous program P prime that we generated from the original sequential program P is the only sound asynchronization in that program is the strong asynchronization, which is some kind of weakening of the problem that we want to compute all asynchronization. So which means that checking whether there exists a sound synchronization that is different from the strong asynchronization is p-space complete. Now, using this reduction now to the problem of the asynchronization synthesis, we developed an approximated solution where we do some data flow analysis. In particular, we transform an original program P to some abstract program P sharp, such that the if statement are changed to some non-deterministic if statement, and the while loop is changing some if non-deterministic if statement. Here you can ask the question why we only unfolded the while loop once. Because of the problem that we are looking at. We are looking at data races, and you cannot have a data race between two unrolling of the while loop because of async has to be inside the while loop body. So using this reduction, we prove that if P bar prime is a sound asynchronization of P bar, then P prime is also a sound asynchronization of the original program. So this is a soundness problem. So how we do this data flow analysis over the new programs? So for every method in this program, we compute a set of variables that are accessed by read or write. And also we compute a new set of variables that we call concurrent accesses, which are accesses, read and write accesses that happen after the first await in that method. Then for every method in this program P bar prime, in bottom-up order, and for each statement in this body of M, if this statement occurs between the call to some method M prime and some await to that method, we check whether there is a conflict between the variables that this method access or this statement access and the variable that are that concurrent accesses in the method M prime. If there is, that means there is a data race and we need to repair it. So here the conflict relation that we defined there between two pairs of read and write statement is as a standard data race checking. We check whether there is a write in the first phase and the write in the first pair that was accessed by a read or write in the second pair. Or if there is a write in the second pair that was accessed by read or write in the first pair. Now, before, like we showed that the precise solution and the exact precise solution is p-space complete. Now, for this abstraction, we can reduce that time complexity to polynomial time. Now we move to an evaluation where we implemented this data flow analysis in a prototype tool. So here we used like the Roslyn.NET compiler to construct a control flow graph for method in C# program. So our benchmark set constitutes of 5 synthetic benchmarks that we manually built, and 9 programs extracted from OpenSUSE C# GitHub application, and 2 programs that we extracted from question on Stack Overflow about async await. So here we have the line of codes, the number of methods in each program, the number of calls, and the number of asynchronous calls. So here is the result of the experiment. So I don't expect you to read all of those columns, but the main takeaway is that with a few exceptions, each program admits multiple sound asynchronizations, which make the focus on the delay complexity relevant. Second, for the synthetic benchmark, we have around 100 possible sound asynchronization, And we see that the time that the data flow analysis takes to compute this one is small. Doesn't get affected as much like when you only have two asynchronization, because most of the time is consumed when you compute the control flow graph and this data point that you access. But finding this asynchronization doesn't take time. To conclude, we presented a framework for refactoring asynchronous program to equivalent, sequential program to equivalent asynchronous program that is based on async awaits. We gave a precise complexity bound for the problem of computing all sound asynchronization. Then we used that reduction to develop an approximated synthesis procedure based on data flow analysis that we implemented and evaluated on C# programs. As a future work, we plan to extend our approach to programs that use async await with explicit multi-threading that include the blocking await primitive, which can result in deadlocks. Note that the programs that we consider here that rely exclusively on async await are deadlock-free by definition. Thank you.
Questions? Now you have to ask a question. You got attention. So okay, let me ask a question. So did you compare with like handwritten, like hand optimized programs? Like for example, where you actually write await by hand and then compare it the speedups with whatever you could get?
Yeah, so here, like for instance, because we focus on the general problem of finding all asynchronization. So this will include the ones that are handwritten. Because if this one that are handwritten are data free, we should return them based on the correct. So we return them. But here, like, the comparison will be like, what kind of performance criteria? Because we show that if your criteria of like more parallelism is based on the number of statements between the await and the call, that's not like, not every program will satisfy that criteria. Because here you need like the context of environment that program will be executed in, how much the IO call will take. And this now you cannot know unless you execute this program in the actual context. Because otherwise you cannot, if you assume some environment that evaluation will be like kind of impacted by your assumption about how much time the IO call will take. Unless you execute it in the actual environment, you cannot decide which one. But focusing on the general problem of finding all asynchronization will eventually like solve that problem, because now you only need to define what are your criteria of like the most performant asynchronization. You give us that, and we have all the program, we need only to enumerate them.
Great. So any other questions from the audience? I think there's a...
I apologize if I missed something right at the beginning of your talk, but the situation you're dealing with seems to me to be exactly the kind of thing that is normally addressed using semaphores or signals and monitors or futures, where you hive off another process to do something and you want to hook up with it later on when you'll finish something else and it's finished what it's doing. Why are you not using a mechanism like that rather than what seems to me like a rather sledgehammer approach of trying to work out all the, how much time these things might take?
I'm not sure if I understand the question exactly, because here, like, we are not introducing new, like, programming paradigm. So this is like async await is a paradigm that is used like in C# and other programming languages to like for those asynchronous like methods to execute them. What we are proposing is just like, let's say if you have some sequential program and you want to use this primitive that are offered by those programming languages to do some factorization. How can you but the first criteria is you don't want to introduce data races. That is the first one. Now, even if you don't want to introduce data races, there's still like a big number of programs that are data race free that are asynchronous. Now, which one of them you want to choose? There is, you need like some kind of dynamic criteria. What we proposed is that since we cannot determine this program statically, we need some procedure to give them to us all, and then we have some dynamic criteria to choose which one of this one that you gave to us is the most performant. So here, what we are looking at is just like the problem of finding all of these programs. What is the complexity of this problem? A naive approach that I presented in the beginning, if you only like look at every program, every asynchronous, check whether it is data race free, this can take you exponential time because there is an exponential number of them.
Yeah, I understand all of the basic of what you're analyzing. I'm just trying to understand why you're doing it in the first place when there are other mechanisms that seem to me to solve the problem.
Which problem
in a
is
much
solved,
more
right?
standard way.
Maybe I'm missing some, because what do you mean, like which problem it's solving? Like the problem of finding all of this asynchronization?
Okay, fine.
I'm not sure.
Okay.
So I was wondering, what are the limitations of your approach? Like you showed us code where you are using the read file task that is probably written in the standard library, right? How far can you go with already implemented code that you don't have like directly inside the code that is given to you?
Okay, so like they're like async, like in the programming languages are very rich. Like you can pass them through like methods as a parameter to other methods. So here, like that problem is already indecidable. Like if you have a sequential program where you can pass like methods pointer through like parameters, so that problem is already decidable. So we even like didn't look at that. We know because even if we reduce it to some kind of reachability in the sequential program, it will still indecidable. So like we have some like this limitation where we limit how much you can like play with the language because otherwise you will reach that limit. Is it clear?
Yeah, I think that answers.
Because like if you look at C#, like you can pass let's say like when you return like when you return the task parameter. So here, let's say you return the task parameter in line 3, T1. That line, that T1, like in C#, you can pass it as a parameter to another function. However, we don't allow that in our language because we know that if you send like this pointer to procedure call through like method calls, you will reach indecidability. So we limit that. We only allow like to use this like task parameter within the function body. But there are still a lot of programs that only allow this.
Okay, thank you. Second question would be, I'm not sure, I think it might be already covered, but you can start two threads after each other, right? And then await both of them in the same method. Did you look at like reordering the awaits?
Okay, the ordering of the awaits.
Yeah, if you start two threads in the same method, basically, right?
Yes.
You can like reorder the awaits.
Yes.
Did you look at that?
So here, like, okay, so we don't do dynamic tests of this. We only try to find all asynchronization. This will include like the every position placement of that await. That will not lead you to a data read. So this includes the like reordering of this await. But for the dynamic test that we did to show that the counter example that you cannot statically define that, we only needed like this toy programs to prove that our argument.
Okay, thank you.
Thank you.
Thank you.